Tonight, we're going to explore a question that sounds simple at first, but becomes more surprising the longer you think about it. What is the hottest place in the universe? At first glance, the answer might seem obvious. You might picture the sun, blazing high in the sky, or perhaps molten lava spilling from a volcano. Maybe you imagine the surface of a distant star glowing white-blue with unimaginable heat. All of those sound like reasonable guesses, but the truth is a little stranger. The hottest places in the universe are not always the ones that look the brightest. Some are hidden in violent cosmic events, others exist only for tiny fractions of a second, and a few of them are so extreme that they push the limits of physics itself. Tonight, we're going to take a slow and careful journey through those places. We'll start with the kind of heat we understand here on Earth, the warmth of sunlight or the heat of a summer afternoon. Then, step by step, we'll travel outward into the wider universe, moving toward environments so hot that atoms break apart and matter behaves in ways that sound almost impossible. But before we wander too far into cosmic furnaces and exploding stars, I'd like to ask you something simple. Where are you listening from tonight? Are you curled up somewhere quiet after a long day? Maybe in your room with the lights dimmed, or under a blanket while the world outside slowly settles down. Perhaps it's late evening where you are. Or maybe you're listening in the early hours of the morning when everything feels a little calmer. And what time is it in your corner of the world right now? It's always a little amusing to think about that. A video like this travels across the planet instantly, yet each of us arrives here at a completely different moment of the day. Some listeners are ending their evening, others are just starting their night. A few might even be listening while the sun is rising somewhere far away. Wherever you are, I'm glad you're here. If you find this kind of slow exploration relaxing or interesting, feel free to give the video a like and perhaps subscribe as well. It helps this quiet little space reach more curious minds who might also enjoy drifting through science at a gentler pace. Now, hopefully this topic won't keep you too awake, although, if it does, at least you'll learn something unusual about the universe before sleep arrives. So go ahead and settle in, let your thoughts slow down, and let's begin with a simple idea: heat. Most of us experience heat every day without thinking about it very much. You feel it when you step outside on a sunny afternoon. You notice it when you hold a warm mug of tea or coffee. In winter, you appreciate it when a room heater starts working after a cold walk outside. Heat is one of those everyday experiences that feels very familiar. Yet the deeper scientists look at it, the more interesting it becomes. When we say something is hot, what we really mean is that the tiny particles inside it, atoms and molecules, are moving quickly. Temperature is simply a measure of how energetic those particles are. The faster they move, the hotter something becomes. Take a pot of water on a stove. As the burner heats the pot, the water molecules begin moving faster and faster. Eventually they move so quickly that they break free from the liquid and turn into steam. Nothing magical happens there, it's just motion at a microscopic level. And that simple idea, particles moving faster and faster, turns out to be the key to understanding the hottest places in the universe. Because if you keep adding energy, particles keep speeding up. If they move fast enough, atoms themselves begin to break apart. Electrons separate from nuclei. Matter becomes a kind of energetic soup called plasma. And if the temperature rises even further, the behaviour of matter changes again. But we're getting ahead of ourselves. Before travelling out into deep space, it helps to consider the range of temperatures we're familiar with here on Earth. Let's start with something comfortable. A pleasant room temperature might be around 20 degrees Celsius, or about 68 degrees Fahrenheit. At that temperature, the atoms in the air around you are moving at hundreds of meters per second, even though you don't notice it. Warm summer days might reach 30 degrees Celsius. Hot deserts can climb past 40. Those temperatures feel intense to us, mostly because our bodies are very good at maintaining a stable internal temperature. Humans function best around 37 degrees Celsius. When the environment gets much hotter than that, it becomes harder for the body to cool itself. But compared to cosmic temperatures, even the hottest places on Earth are surprisingly mild. Consider lava flowing from a volcano. Molten rock can reach around 1000 degrees Celsius. Standing near it feels like standing beside a giant open oven. That's already far beyond anything comfortable for living creatures, and yet 1000 degrees is still small compared with the heat of stars. The surface of our sun, for example, is about 5,500 degrees Celsius. At that temperature, matter behaves very differently from the solid rocks and liquids we're used to. The Sun is made mostly of plasma, a state of matter where electrons are no longer tightly bound to atoms, but even the Sun's surface is not the hottest part of it. Deep in the Sun's core, temperatures climb to roughly 15 million degrees Celsius. That enormous heat allows hydrogen atoms to fuse together, releasing energy that eventually becomes sunlight. Every beam of sunlight that warms your skin began its journey in that furnace at the centre of our star. Even so, the Sun is not the hottest star in the universe. Far from it. There are stars many times hotter. Some massive blue stars have surface temperatures of 30,000 degrees Celsius or more. These stars burn brighter and hotter because their immense gravity squeezes their cores harder, allowing nuclear reactions to occur at faster rates. Yet as extreme as those numbers sound, they still don't come close to the most intense temperatures known in the cosmos. Because stars, it turns out, are only one step along a much larger scale. Elsewhere in the universe, there are events where matter becomes far hotter than the surface of any star. Exploding stars, collapsing stellar cores, and swirling disks of gas around black holes can all reach temperatures that push far beyond what most people imagine. Some of those environments heat matter to billions of degrees. Others briefly reach trillions, and one of the hottest conditions ever created didn't occur in space at all. It happened here on Earth. But before we reach that moment, it helps to take a closer look at what temperature actually measures. Because temperature, despite feeling simple, is one of the most useful tools scientists have for understanding the universe. Every object around you has a temperature. Your room, the air outside, the distant moon, even the empty space between galaxies has a measurable temperature, although it is extremely cold. In physics, temperature tells us something about energy distribution among particles. When energy is added to a system, particles move faster or vibrate more strongly. When energy is removed, their motion slows. This idea applies everywhere, from a cup of tea cooling on a table to entire galaxies, interacting across millions of light years. But measuring extreme temperatures is not always easy. You can't exactly place a thermometer into the core of a star. Instead, scientists rely on indirect methods. They study the light emitted by hot objects, analyse radiation patterns, and use physics equations to estimate temperatures from observed behaviour. For example, very hot objects emit light at specific wavelengths. By studying that light, astronomers can determine how energetic the particles must be, which reveals the temperature. In other situations, scientists observe how matter behaves under extreme conditions. If particles are moving with certain energies or colliding in specific ways, those interactions can also reveal temperature. These techniques allow researchers to estimate temperatures across the entire universe, from frozen clouds of gas drifting between stars, only a few degrees above absolute zero, to violent explosions where matter becomes so energetic that atomic structure barely survives. So when we ask about the hottest place in the universe, we're really asking where particles are moving with the greatest energy. And the answer turns out to be more surprising than simply pointing to a star or a galaxy. Some of the hottest environments occur during brief cosmic events. A star collapsing into a neutron star, for example, releases enormous amounts of energy. During those moments, temperatures can climb to extraordinary levels. Similarly, when matter spirals into a black hole, it forms an accretion disk, a swirling ring of gas heated by intense friction and gravity. Those disks can reach temperatures of tens of millions of degrees. That's already far hotter than the Sun's surface. But even those environments are not the ultimate champions of heat, because there are places where the universe briefly reaches temperatures that approach the conditions present shortly after the Big Bang itself. And strangely enough, one of those places exists in enormous underground laboratories where scientists smash particles together at incredible speeds. Those experiments recreate tiny flashes of the early universe, producing temperatures far beyond anything naturally found in our solar system. We'll get to that in a while. For now, though, it helps to keep our journey grounded in something familiar. Because before we explore collapsing stars, black holes, and the hottest matter ever created, it's worth thinking about the way humans experience heat here on Earth. After all, the concept of temperature only became meaningful to us because we could feel warmth and cold long before we understood physics. Humans have always been aware of heat. The warmth of fire helped our ancestors survive cold nights. The heat of the sun allowed crops to grow. The absence of warmth during winter shaped entire cultures and migrations. Long before thermometers existed, people could sense temperature through touch and experience, and over time, that everyday experience slowly evolved into the scientific idea we now call temperature. Understanding how we perceive heat is actually an important step toward understanding how scientists measure it across the universe. Because the way our bodies interpret warmth and cold reveals something about the limits of our perception. For example, what feels extremely hot to us might be only a small increase in temperature on a cosmic scale. A summer heat wave might push temperatures to 40 degrees Celsius. That feels intense. But compared with stellar temperatures, that difference is barely noticeable. It's similar to the difference between walking speed and the speed of light. Both involve motion, but the scales are vastly different. The same is true for heat. A simple way to begin thinking about heat is to remember that long before thermometers, satellites or physics equations existed, humans were already experts at feeling it. You don't need any scientific instruments to know when something is warm. Your skin tells you immediately. Step into sunlight on a cool morning, and the warmth feels pleasant. Touch a metal pan that has been sitting on a hot stove, and you will pull your hand back in a fraction of a second. Walk outside on a summer afternoon when the air feels thick and heavy, and you instinctively slow down, searching for shade. For most of human history, that kind of sensory experience was the only way people understood temperature. Warmth meant comfort. Cold meant danger. Heat could cook food, soften metal, and keep predators away at night. But too much heat could also destroy things. Forest fires, droughts, and scorching deserts reminded early civilizations that warmth was both a gift and a force to be respected. Even today, despite all the advanced tools we have for measuring temperature, our first encounter with heat is still personal and immediate. It begins with the body. Your skin is covered with tiny nerve endings that detect temperature changes. These specialized receptors respond when the environment around you becomes warmer or colder. They send signals through the nervous system to the brain, which then interprets the sensation. That is why you feel warmth almost instantly when holding a mug of hot tea. The molecules in the cup are vibrating more quickly than the molecules in your hand, and that energy begins to flow from the hotter object into your skin. Your nerves notice the difference and report it. From a physics perspective, heat is simply energy moving from a warmer place to a cooler one. But from the perspective of a person sitting quietly in a room, it feels much more like a sensation than a transfer of energy. Your body, interestingly enough, is constantly managing heat whether you notice it or not. Humans function best within a very narrow internal temperature range. The average human body maintains a temperature of about 37 degrees Celsius. That number may vary slightly depending on activity level, time of day, or even individual biology, but the general range remains surprisingly stable. To keep things that way, the body uses several built-in systems. When you become too warm, your body begins sweating. Tiny droplets of water appear on the skin and slowly evaporate into the air. That evaporation removes heat, cooling the surface of the body. At the same time, blood vessels near the skin expand, allowing more warm blood to circulate close to the surface where heat can escape into the surrounding air. When you become cold, the opposite happens. Blood vessels near the skin tighten, conserving heat by keeping warm blood deeper inside the body. Muscles may also begin to contract rapidly in the form of shivering, which produces additional heat through movement. All of this happens automatically, without any conscious effort. You might simply notice that you feel hot, or cold, or comfortable. Behind the scenes, your body is constantly adjusting. These small biological responses shape the way humans perceive temperature. Because our bodies operate within such a narrow thermal range, even modest changes in the environment can feel dramatic. A room that is 22 degrees Celsius might feel comfortable. If the temperature rises to 30, the difference feels intense. Yet on a cosmic scale, both of those numbers are extremely close to one another. Still, for humans, those few degrees matter a great deal. Think about the experience of stepping outside during different seasons. In winter, when cold air touches your skin, the sensation can feel sharp and immediate. Breath becomes visible as warm air from the lungs meets the colder atmosphere. Fingers stiffen. Shoulders rise slightly as the body instinctively tries to conserve warmth. Then there is the opposite experience. A summer afternoon when the sun stands high in the sky and heat radiates from pavement and buildings. The air feels thick, movement slows, even standing still can feel like work. What you're experiencing in those moments is the interaction between your body and the surrounding environment as energy moves between them. And on Earth, the largest source of that energy is the sun. Nearly all warmth on our planet begins with sunlight. The sun releases enormous amounts of energy in every direction. Only a small fraction of that energy reaches Earth, but it is more than enough to power weather systems, ocean currents, plant growth, and the delicate temperature balance that allows life to exist. Sunlight travels through space as electromagnetic radiation. When it reaches Earth, some of it is reflected back into space by clouds and ice. The rest is absorbed by land, water, and atmosphere. Once absorbed, that energy becomes heat. The ground warms, air currents begin to move, oceans slowly store and release thermal energy across seasons. In a sense, the warmth you feel on a sunny afternoon is the final step in a long journey that began deep inside the sun millions of years ago. But the experience of heat on Earth is not just about sunlight. Geography also plays a role. Different regions of the planet absorb and release heat in different ways. Deserts, for example, are famous for extreme temperatures. During the day, the ground absorbs large amounts of solar radiation. Sand and rock heat quickly because they contain little moisture to slow the process. Temperatures can climb above 50 degrees Celsius in some locations, yet at night, deserts cool rapidly. Without clouds or water vapor to trap heat, energy escapes back into space. A scorching desert afternoon can turn into a surprisingly cold night within hours. Oceans behave differently. Water warms more slowly than land because it has a higher heat capacity. That means it takes more energy to raise its temperature. As a result, coastal regions often experience milder climates. The ocean acts like a giant thermal reservoir, absorbing heat during warm periods and releasing it gradually when temperatures drop. This steady exchange of heat between land, water, and atmosphere creates the weather patterns we experience every day. Wind carries warm air from one region to another. Ocean currents transport heat across entire continents. Clouds trap heat during the night and reflect sunlight during the day. Even something as simple as standing in the shade beneath a tree is part of that larger system. Shade works because objects block sunlight before it can reach you. Without direct radiation from the sun, the air and ground around you transfer less heat into your body. The difference might only be a few degrees, but to human senses it can feel dramatic. Throughout history, people have adapted to these temperature patterns in creative ways. Architecture in hot climates often includes thick walls, narrow streets, and shaded courtyards that help reduce heat exposure. In colder regions, homes are designed to trap warmth and minimize heat loss. Clothing choices also reflect the need to manage temperature. Light fabrics allow air circulation in warm climates. Insulated layers help retain heat in colder ones. All of these strategies are part of humanity's long relationship with heat. Fire, perhaps more than anything else, changed that relationship permanently. When early humans learned to control fire, they gained the ability to create heat wherever they needed it. Fire provided warmth during cold nights, protection from animals, and a way to cook food. Cooking itself transformed human diets. Heat breaks down tough plant fibers and proteins, making food easier to digest and unlocking more nutrients. Some anthropologists believe that the regular use of fire played a role in the development of larger human brains by improving energy intake. A small flame might not seem very impressive today, especially in a world filled with electric stoves and modern heating systems. Yet in ancient times, fire represented control over one of nature's most powerful forces. Even now, fire remains one of the hottest phenomena most people will encounter directly. A typical campfire burns at temperatures between 600 and 1000 degrees Celsius. Industrial furnaces can reach much higher temperatures, sometimes exceeding 2000 degrees Celsius depending on the fuel and design. Those temperatures are enough to melt many metals and reshape materials, and yet, compared with the heat found in stars, even the hottest furnace on Earth is relatively mild. This contrast between everyday heat and cosmic heat is one of the most fascinating aspects of astrophysics. The warmth you feel on your skin from sunlight comes from a star whose surface temperature is thousands of degrees. But even that star is not the hottest object in the universe. Far from it. Before we venture out toward those extreme environments, there is one more important idea worth considering. Human perception of heat is not perfectly reliable. Two objects at the same temperature can feel very different when touched. For example, a metal chair and a wooden chair sitting in the same room will both be at room temperature. Yet when you touch them, the metal often feels colder. This happens because metal conducts heat more efficiently than wood. When your hand touches metal, heat from your skin moves quickly into the material, creating the sensation of cold. Wood transfers heat more slowly, so it feels warmer even though its temperature is identical. The same principle explains why walking barefoot on tile floors feels cooler than walking on carpet. Your senses are detecting the rate at which heat moves, not just the temperature itself. Because of this, humans eventually developed tools to measure temperature more accurately. Thermometers allowed scientists to quantify heat, rather than simply describe it. Early thermometers used expanding liquids such as mercury or alcohol. As temperature increased, the liquid expanded along a calibrated tube. Later technologies introduced electronic sensors capable of detecting extremely small temperature changes. Today, scientists use instruments far more sophisticated than those early devices. Infrared cameras can measure heat from a distance by detecting thermal radiation. Satellites monitor temperature patterns across entire planets. Sensitive detectors can even measure the faint heat left over from the early universe itself. These tools allow researchers to compare temperatures across enormous ranges, from the cold darkness between galaxies to the blazing interiors of stars. But all of those measurements trace back to the same fundamental idea. Temperature reflects the energy of moving particles. That simple concept links the warmth of sunlight on your skin to the most extreme environments in the cosmos. And once scientists understood that connection, it became possible to ask a much larger question. If heat comes from particles moving faster and faster as energy increases, then somewhere in the universe there must be places where those particles move with incredible energy. Places where atoms are torn apart, places where matter glows with blinding intensity, places where the word hot barely captures what is happening. To explore those environments, scientists first had to develop reliable ways to measure temperatures far beyond anything experienced on Earth. At some point in history, people began to realize that warmth and cold were not just sensations. They were physical properties of the world that could be studied, measured, and understood. For a very long time, heat was mysterious. Ancient thinkers had many ideas about what it might be. Some believed warmth came from a special substance that flowed between objects. Others imagined heat as a kind of invisible fluid that filled materials and escaped when something cooled down. Those ideas sound unusual now, but they made sense at the time. When a metal rod becomes hot on one end and gradually warms along its length, it can feel as though something is travelling through it. Eventually, though, experiments revealed a simpler explanation. Heat is not a substance. Heat is energy in motion. More specifically, temperature reflects how quickly the tiny particles inside matter are moving. Every solid, liquid, and gas is made of atoms and molecules that are constantly vibrating, spinning, or bouncing around. Even objects that feel perfectly still are filled with microscopic activity. When those particles move slowly, the temperature is low. When they move faster, the temperature rises. This idea may seem straightforward, but it took centuries of observation and experimentation before scientists fully accepted it. One reason is that the motion involved is incredibly small. You cannot see atoms moving with the naked eye, so for most of human history their behaviour remained hidden. Once scientists began developing tools to study matter at smaller scales, the picture became clearer. Consider a simple glass of water sitting on a table. From a distance it appears calm and motionless, but at the microscopic level, every molecule in that water is constantly jostling its neighbours. They collide, change direction, and bounce apart again, millions of times every second. If the water is cold, the molecules move relatively slowly. If the water is heated, they move more quickly and collide with greater energy. Continue heating the water, and eventually those molecules move fast enough to escape from the liquid entirely. That is when water begins to boil and turn into steam. The same basic principle applies to almost everything in the universe. Temperature is simply a measure of how energetic particles are within a system. This understanding led scientists to develop a precise language for describing heat. One important distinction is the difference between heat and temperature. In everyday conversation, The two words often mean the same thing, but in physics they represent different ideas. Temperature describes how energetic the particles are on average. Heat refers to energy being transferred from one object to another because of a temperature difference. If you place a warm cup of tea on a cool table, energy flows from the tea into the surrounding air and into the table itself. That transfer of energy is heat. The tea's temperature slowly drops as the particles inside lose energy. Meanwhile, the surrounding environment warms slightly. This exchange continues until everything reaches the same temperature. At that point, the system is said to be in thermal equilibrium. This concept appears everywhere in nature. Objects that come into contact gradually share energy until their temperatures balance out. It is the same reason ice melts when dropped into warm water. Energy moves from the warmer liquid into the colder ice, causing the solid structure of ice crystals to break apart. In the process, the water cools and the ice warms until both reach the same temperature. Understanding this energy transfer allowed scientists to develop thermodynamics, the branch of physics that studies heat and energy. Thermodynamics explains not only how temperature works, but also how energy flows through engines, weather systems, stars, and even living organisms. One of the most useful ideas in thermodynamics is the concept of absolute zero. Absolute zero represents the lowest possible temperature in the universe. It occurs when particles contain the smallest amount of motion physically allowed. On the Celsius scale, absolute zero is negative 273 degrees. On the Kelvin scale, which scientists often use in physics, absolute zero is defined as 0 Kelvin. The Kelvin scale is convenient because it begins at the lowest possible temperature. There are no negative numbers. Every temperature represents a specific amount of particle motion above absolute zero. For example, room temperature is roughly 293 Kelvin. The surface of the Sun is around 5,800 Kelvin. And many of the hottest phenomena in the universe reach temperatures of billions or even trillions of Kelvin. When temperatures reach those levels, matter behaves in ways that seem almost impossible compared with everyday experience. Atoms themselves can no longer remain intact. Electrons break free from atomic nuclei, creating plasma, a state of matter where charged particles move freely in an energetic mixture. Plasma is actually the most common state of matter in the universe. Stars are made of plasma. Lightning is a brief flash of plasma. Even glowing auroras in the polar skies are caused by energetic plasma interacting with Earth's atmosphere. Yet despite its abundance across the cosmos, plasma rarely appears in everyday life on Earth. Most objects around us exist as solids, liquids or gases because temperatures here are relatively moderate. To reach the conditions where plasma dominates, enormous amounts of energy are required. And that leads to an interesting realization. The hottest places in the universe are not simply places with fire or glowing surfaces. They are places where energy is concentrated to such extremes that matter itself begins to break apart. Another useful way to understand temperature is through the idea of kinetic energy. Kinetic energy is the energy of motion. If you throw a ball, the ball carries kinetic energy because it is moving. When the ball hits something and stops, that energy transfers into the object it strikes or into the surrounding environment. Particles inside matter behave in a similar way, although on a much smaller scale. Atoms and molecules vibrate, spin, and collide with one another. Each motion carries kinetic energy. Temperature represents the average kinetic energy of those particles. When energy is added to a system, particle motion increases. When energy is removed, motion decreases. This connection between motion and temperature allows scientists to calculate temperature even in environments where traditional thermometers would never survive. Astronomers, for example, can estimate the temperature of distant stars by analysing the light they emit. Hot objects tend to glow with specific colours depending on their temperature. A relatively cool star may appear red or orange. A hotter star glows white. The hottest stars shine blue. This colour pattern occurs because atoms in hot environments emit radiation at different wavelengths depending on how energetic they are. By studying those wavelengths, astronomers can estimate stellar temperatures even across vast distances. Another method involves studying the behaviour of particles in extreme environments. For instance, when gas spirals toward a black hole, it accelerates to enormous speeds. Friction and gravitational compression heat the gas dramatically. The resulting radiation carries information about temperature. Observations of this radiation allow scientists to estimate just how hot the gas becomes as it falls toward the black hole. In some cases, the temperatures involved reach tens of millions of degrees. Even those numbers, impressive as they sound, are still far below the most extreme temperatures ever observed. There is also a fascinating relationship between temperature and energy density. Energy density refers to how much energy exists within a given amount of space. When enormous amounts of energy are squeezed in tiny volumes, temperatures rise dramatically. This principle explains why events like supernova explosions can reach extraordinary temperatures. When a massive star collapses under its own gravity, enormous energy becomes concentrated in a small region. The sudden compression causes matter to heat intensely before the star explodes outward. During those moments, temperatures can climb into the billions of degrees, but the scale of heat in the universe does not stop there. Particle physics experiments on Earth have produced even higher temperatures, briefly recreating conditions similar to those that existed just after the Big Bang. Inside enormous particle accelerators, atoms are smashed together at incredible speeds. These collisions release vast amounts of energy in tiny spaces, heating the resulting particles to trillions of degrees. Such temperatures exist for only fractions of a second, but they reveal something remarkable about the nature of matter. Under those conditions, even protons and neutrons begin to break apart into their fundamental components. The universe briefly returns to a state similar to the one it experienced in its earliest moments. Understanding temperature in this way also helps scientists compare vastly different environments. The core of the Sun might reach 15 million degrees. A supernova explosion may reach billions. Particle collisions in laboratories can exceed several trillion degrees, and theoretical models suggest that the earliest fractions of a second after the Big Bang were hotter still. At that time, temperatures were so extreme that the laws of physics themselves behaved differently from the way we observe them today. But before considering those early moments of the universe, there is another important question to explore. If heat is simply energy moving between objects, how do scientists measure temperatures in places that are unimaginably far away? After all, no one can travel to the surface of a distant star with a thermometer in hand. Astronomers rely on careful observation and clever techniques to estimate temperatures across space. By studying light, radiation, and particle behaviour, they can determine how energetic distant environments must be. This process allows scientists to map temperatures throughout galaxies, star systems, and interstellar clouds. Through these methods, researchers have gradually identified some of the most extreme thermal environments in existence. But measuring those temperatures requires tools far more sophisticated than the simple thermometers once used to study everyday weather. Understanding temperature becomes much more complicated once we move beyond everyday objects. A thermometer works perfectly well for measuring the warmth of the air in your room or the temperature of water on a stove. But the universe is filled with environments where no instrument could survive long enough to take a reading. The surface of a star would melt any probe instantly. The gas spiralling around a black hole would tear apart most materials long before they could measure anything. So scientists had to find another way. Instead of touching these environments directly, they learned to read the signals that hot matter naturally sends into space. Heat does not remain hidden. Whenever particles move with enough energy, they release radiation. That radiation travels outward in the form of light or other electromagnetic waves, carrying information about the conditions where it was produced. In other words, hot objects announce their temperature through the energy they emit. This idea is one of the most powerful tools in astronomy. By observing the light from distant objects, scientists can estimate temperatures across the universe without ever travelling to those places. The method works because of a simple relationship between heat and radiation. Any object with a temperature above absolute zero emits electromagnetic radiation. The amount and type of radiation depend on how energetic the particles inside that object are. Warmer objects release radiation with shorter wavelengths and higher energy. Cooler objects emit longer wavelengths with less energy. You experience a small part of this effect every day. If you place your hand near a warm surface without touching it, you can sometimes feel heat radiating toward your skin. That sensation comes from infrared radiation, a form of light that our eyes cannot see, but our bodies can detect as warmth. Many animals can sense infrared radiation even more effectively than humans. Some snakes, for example, use specialized heat-sensitive organs to locate warm-blooded prey in the dark. The prey does not glow visibly, but its body temperature produces infrared radiation that the snake can detect. Scientists have developed instruments that work on a similar principle. Infrared cameras allow us to visualize heat differences in everyday environments. Buildings, engines, animals, and even human bodies appear as glowing patterns when viewed through these devices. Warmer areas emit stronger infrared signals and appear brighter in the image. Now imagine applying that idea to the entire universe. Astronomers use telescopes designed to detect different kinds of radiation, including infrared, visible light, ultraviolet radiation, X-rays, and gamma rays. Each type of radiation corresponds to different energy levels and therefore different temperature ranges. Cooler objects in space often emit mostly infrared radiation. Dust clouds between stars, for example, may be extremely cold by human standards, sometimes only a few dozen degrees above absolute zero. These clouds glow faintly in infrared wavelengths, allowing astronomers to map their structure even though they appear completely dark to visible light telescopes. Hotter objects emit radiation at shorter wavelengths. Stars like our Sun radiate strongly in visible light because their surfaces are thousands of degrees hot. Extremely hot environments such as supernova remnants or gas falling into black holes can emit intense X-rays or even gamma rays. Those forms of radiation are so energetic that they cannot pass through Earth's atmosphere easily, which is why many telescopes designed to observe them must operate in space. By studying the wavelengths and intensity of radiation coming from an object, scientists can estimate its temperature. The process involves analysing what is called a spectrum. When light from a star or other object is spread out into its component wavelengths, it forms a spectrum, similar to how sunlight passing through a prism produces a rainbow. Each colour or wavelength carries information about the physical conditions of the source. Some parts of the spectrum appear brighter than others. Certain wavelengths may be missing entirely. These patterns reveal details about the temperature, chemical composition, and motion of the object emitting the light. Hotter objects tend to produce spectra that peak at shorter wavelengths. Cooler ones peak at longer wavelengths. By identifying where that peak occurs, astronomers can calculate an approximate temperature. This method works even across enormous distances. A star hundreds of light years away might look like a tiny point of light through a telescope, but its spectrum can still reveal whether its surface temperature is 3,000 degrees or 30,000 degrees. Another useful technique involves studying the motion of particles. In some regions of space, gas becomes so hot that its atoms and electrons move at tremendous speeds. These particles collide with each other constantly, producing radiation as they interact. By observing that radiation and understanding how fast the particles must be moving to produce it, scientists can estimate the temperature of the gas. This approach is often used when studying extremely hot environments such as supernova remnants. When a massive star explodes, its outer layers are thrown outward at incredible speeds. Shock waves travel through the surrounding gas, compressing and heating it dramatically. The resulting cloud of debris glows in X-rays because the particles inside are moving with such high energy. By measuring those X-rays, astronomers can estimate temperatures reaching millions of degrees. One particularly interesting case involves gas near black holes. As matter falls toward a black hole, it rarely plunges straight in. Instead, it forms a rotating disk around the black hole called an accretion disk. Friction between particles in the disk converts gravitational energy into heat. The gas becomes incredibly hot as it spirals inward. Temperatures in these disks can climb into the tens of millions of degrees. At those levels, the gas emits strong X-rays. Space-based observatories designed to detect X-rays allow astronomers to study these disks in remarkable detail. From Earth, the black hole itself remains invisible because not even light can escape its gravity. But the glowing disk of superheated gas surrounding it reveals that something extraordinary is happening there. Scientists also measure temperature in environments where radiation is not the only clue. In laboratories on Earth, particle accelerators allow researchers to recreate extremely energetic conditions by colliding atoms together at high speeds. When two atomic nuclei smash into each other at nearly the speed of light, the energy released in the collision briefly produces temperatures far higher than anything found in ordinary environments. Those collisions create tiny bursts of matter that behave very differently from normal atoms. For a fraction of a second, particles exist in a state known as quark-gluon plasma, where the building blocks of protons and neutrons move freely instead of remaining bound together. By studying how these particles scatter and decay, scientists can estimate the temperature of the collision. Some experiments have reached temperatures of several trillion degrees Celsius, hotter than the interior of any star. Although those conditions last for only tiny fractions of a second, they provide valuable insight into how matter behaved shortly after the universe began. There is also another remarkable way scientists detect heat across space, by observing how hot objects affect their surroundings. Hot gas expands. It pushes against nearby material and creates pressure differences that influence motion. In galaxies, clusters of galaxies, and enormous cosmic structures, astronomers can observe how hot plasma moves and interacts with gravity. For example, clusters of galaxies contain vast clouds of extremely hot gas filling the space between galaxies. This gas can reach temperatures of tens of millions of degrees. It emits X-rays that reveal the structure of the cluster and the distribution of matter within it. By mapping these X-ray emissions, scientists learn not only about temperature but also about the gravitational forces shaping the cluster. The ability to detect heat from such distant environments might seem almost magical, but it relies on careful observation combined with physical laws that apply everywhere in the universe. Radiation travels through space at the speed of the light, carrying information about its source across enormous distances. When that radiation finally reaches telescopes on Earth or in orbit, it still contains clues about the temperature and conditions where it began. This approach allows astronomers to study objects billions of light years away and still estimate their temperatures with surprising accuracy. One interesting consequence of this method is that the universe contains temperature extremes far beyond anything we experience on Earth. Cold regions of space can approach just a few degrees above absolute zero, colder than any natural environment on our planet. Meanwhile, certain cosmic events produce heat so intense that ordinary matter breaks apart completely. Understanding how to measure those extremes allows scientists to map the thermal landscape of the cosmos. Some places glow softly with faint warmth. Others blaze with radiation so energetic that it can strip atoms apart. Look up at the sky on a clear day, and the most powerful source of heat in our part of the universe is right there, shining quietly above everything else. The sun appears calm from a distance. It rises in the morning, moves slowly across the sky, and disappears below the horizon in the evening. For most of human history, it seemed like a steady lamp hanging overhead, but the calm appearance is misleading. The sun is an enormous nuclear furnace operating on a scale that is difficult to imagine. Nearly all the warmth that reaches Earth begins its journey deep inside that star. Every breeze, every ocean current, every green leaf growing towards sunlight traces its energy back to reactions happening far beneath the sun's glowing surface. To understand how hot the universe can become, it helps to begin with the nearest star we know well. The sun sits about 150 million kilometers away from Earth. That distance might sound large, but in astronomical terms it is extremely close. Light leaving the sun takes only about 8 minutes to reach us. If the sun were to vanish suddenly, the sky would remain bright for 8 more minutes before darkness finally arrived. From that distance, the sun looks like a simple glowing disk. Through telescopes, however, its surface reveals a constantly shifting landscape of bright regions, darker patches, and enormous loops of glowing gas arcing into space. All of that activity comes from the intense heat inside the star. The sun formed roughly 4.5 billion years ago when a cloud of gas and dust collapsed under gravity. As the cloud shrank, the material at its centre became denser and hotter. Eventually the temperature rose high enough for nuclear fusion to begin. Nuclear fusion is the process that powers stars. In simple terms, fusion occurs when atomic nuclei collide with enough energy to merge together. In the sun's core, hydrogen nuclei combine to form helium. During this process, a small amount of mass is converted directly into energy. That energy becomes the heat and light the sun releases into space. The temperatures required for this reaction are extraordinary. At the sun's centre, temperatures reach about 15 million degrees Celsius. At those levels, atoms no longer exist in the familiar way we encounter them on Earth. The intense heat strips electrons away from nuclei, creating a dense plasma where charged particles move freely. Inside that plasma, hydrogen nuclei move so quickly that collisions happen constantly. Most collisions simply bounce the particles apart again, but occasionally two nuclei come close enough to fuse. When that happens, energy is released and the fusion chain continues. Every second, the Sun converts around 600 million tons of hydrogen into helium. In the process, about 4 million tons of mass transform into energy, according to Einstein's famous equation, E equals mc squared. That energy begins a long journey outward. Photons created in the Sun's core do not travel straight to the surface. The interior of the Sun is extremely dense, so photons collide with particles repeatedly. Each collision sends the photon in a new direction. The path becomes a complicated random walk that can take hundreds of thousands of years before the energy finally reaches the outer layers. By the time the energy reaches the surface, it has spread through the star's enormous volume and cooled dramatically compared with the core. The surface of the Sun, known as the photosphere, has a temperature of about 5,500 degrees Celsius. That may sound modest compared with the core, but it is still hot enough to produce the bright visible light we see from Earth. The photosphere is the layer of the Sun that emits most of the light that reaches our planet. When you look at the Sun, you are seeing radiation from this glowing surface. Even this relatively thin layer is far more energetic than anything found naturally on Earth. At 5,000 degrees, matter exists as plasma rather than solid or liquid. Hydrogen atoms are partially ionized, meaning electrons are no longer tightly bound to their nuclei. The result is a churning sea of charged particles constantly interacting with intense magnetic fields. One of the most striking features visible on the Sun's surface is the presence of sunspots. Sunspots appear as dark patches scattered across the photosphere. They look dark only because they are cooler than the surrounding regions, although even the cooler temperature of a sunspot is around 4,000 degrees Celsius. These spots form when powerful magnetic fields emerging from the Sun's interior suppress the normal flow of hot material from below. Without that upward flow, the surface in that area cools slightly compared with its surroundings. Sunspots often appear in groups and can grow large enough to swallow several Earths side by side. Their presence reveals the complicated magnetic activity happening inside the star. Above the photosphere lies another layer called the chromosphere. This region glows faintly and appears reddish when viewed through specialized instruments. Temperatures there begin to rise again, climbing into the tens of thousands of degrees. Higher still is the Sun's corona, the outermost atmosphere of the star. The corona is one of the most surprising parts of the Sun. Even though it lies farther from the core where the energy originates, it is much hotter than the surface below it. Temperatures in the corona can reach 1 to 2 million degrees Celsius. This seems counterintuitive. Normally you would expect temperatures to decrease as you move away from a heat source, yet the Sun's outer atmosphere becomes hotter instead. Scientists believe this occurs because of the Sun's magnetic fields. Twisting and snapping magnetic field lines release bursts of energy that heat the surrounding plasma to extreme temperatures. The corona stretches millions of kilometers into space. During total solar eclipses, when the moon blocks the bright disk of the Sun, the corona becomes visible as a glowing halo surrounding the dark silhouette. Even though the corona is incredibly hot, it is also extremely thin. The particles there are spread far apart, so the total amount of heat you would feel within it would actually be small compared with standing near a campfire on Earth. Still, the temperature of the corona plays an important role in shaping the solar system. Particles from the corona stream outward continuously in a flow known as the solar wind. This stream of charged particles travels through space and interacts with planets, moons, and magnetic fields throughout the solar system. When the solar wind reaches Earth, our planet's magnetic field deflects most of the particles. Some, however, are guided toward the polar regions where they collide with atoms in the upper atmosphere. These collisions create the glowing curtains of light known as auroras. Auroras appear as green, red, or purple waves shimmering across the night sky. Their beauty hides the energetic interactions between solar particles and Earth's atmosphere. The Sun occasionally produces more dramatic bursts of energy. Solar flares occur when magnetic fields near sunspots suddenly release enormous amounts of stored energy. During a flare, radiation across the electromagnetic spectrum surges outward. Some flares are accompanied by coronal mass ejections, giant clouds of plasma hurled into space. These events can accelerate particles to extremely high speeds and raise local temperatures to tens of millions of degrees. If directed toward Earth, such eruptions can interfere with satellites, radio communications, and electrical systems. Fortunately, our planet's magnetic field shields us from most of their direct effects. Despite its enormous energy output, the Sun is actually considered an average star. There are many stars in the galaxy that are hotter, larger, and more energetic. Some burn through their nuclear fuel much more quickly than the Sun, producing far greater heat and brightness. The Sun's relative stability is one of the reasons life has been able to develop on Earth. Stars far more massive than the Sun tend to live shorter, more violent lives. Their cores burn hotter and faster, leading eventually to explosive endings that scatter heavy elements across space. Those elements later become the building blocks of planets, oceans, and living organisms. In that sense, even the heat of the Sun is part of a much larger cosmic cycle. Energy produced in stellar cores spreads across galaxies, shaping the environments where new stars and planets eventually form. The Sun may feel unimaginably hot compared with anything on Earth, but it represents only a middle step in the scale of cosmic temperatures. Its surface reaches thousands of degrees. Its core reaches millions. If the Sun already seems unimaginably hot, it may come as a surprise that many stars burn at temperatures far beyond it. Our star feels intense because it is the closest one we know, yet across the galaxy there are stars whose surfaces are several times hotter, and whose energy output dwarfs anything happening in our solar system. The Sun belongs to a category astronomers call a yellow dwarf. The name might sound modest, but it simply refers to a star of moderate size and temperature. On the stellar scale, yellow dwarfs sit somewhere in the middle. They are hotter than small red stars, but cooler than the most massive blue ones. When astronomers classify stars, temperature plays a central role. Stars are grouped into spectral classes based largely on how hot their surfaces are and what kinds of light they emit. These categories run from the coolest stars, which glow faintly red, all the way up to the hottest stars that shine with brilliant blue light. Red stars, often called red dwarfs, have surface temperatures of roughly 3,000 degrees Celsius. They burn slowly and steadily, using their fuel at a relaxed pace. Some of these stars may live for hundreds of billions of years, far longer than the current age of the universe. Our Sun, at around 5,500 degrees Celsius on its surface, falls into a warmer category. But above that range are stars whose temperatures rise dramatically. White stars can reach around 10,000 degrees Celsius. Their intense brightness makes them easy to spot even across large distances. And then there are the blue stars. These are among the hottest normal stars in the universe. Their surfaces can reach temperatures of 20,000, 30,000, or even 40,000 degrees Celsius. At those temperatures, the radiation they emit shifts toward the blue and ultraviolet part of the spectrum. Blue stars shine with a dazzling brightness that can outshine the Sun tens of thousands of times over. The reason these stars burn so hot comes down to mass. Massive stars experience much stronger gravitational forces at their cores. That gravity squeezes the stellar material with enormous pressure, raising temperatures high enough for nuclear fusion to proceed much faster than it does in smaller stars. In a star like the Sun, hydrogen fusion occurs at a steady pace. The energy released balances gravity, keeping the star stable for billions of years. In massive stars, however, the stronger gravity pushes the core temperature much higher. Nuclear reactions accelerate dramatically. The star releases energy at a much greater rate, causing it to glow brighter and hotter. But there is a trade-off. Stars that burn hotter also consume their fuel far more quickly. A star several times the mass of the Sun might shine with thousands of times the brightness, yet it may live only a few million years before exhausting its core fuel. In cosmic terms, that is an extremely short lifespan. One famous example of a massive blue star is Rigel, located in the constellation Orion. Rigel shines with a brilliant blue-white colour visible even to the naked eye from Earth. Its surface temperature is roughly 12,000 degrees Celsius, more than twice that of the Sun's surface. Despite being hundreds of light years away, Rigel appears bright in the night sky because it releases an enormous amount of energy. Stars even hotter than Rigel exist in the upper ranges of the stellar classification system. Some of the hottest stars are known as O-type stars. Their surfaces can exceed 40,000 degrees Celsius. These stars are rare but incredibly powerful. Their intense radiation can strip electrons from nearby atoms, creating large glowing regions of ionized gas in surrounding space. These regions, known as emission nebulae, often appear as colourful clouds in astronomical images. The heat and radiation from nearby massive stars energize the gas within the nebula, causing it to glow. In many ways, these hot stars act like cosmic engines shaping their environments. The strong radiation they emit pushes away surrounding gas and dust. Their stellar winds, streams of charged particles flowing outward from their surfaces, can reach speeds of thousands of kilometers per second. Over time, these winds carve cavities in nearby clouds of interstellar material. Within those clouds, new stars are forming. The intense heat from massive stars influences that process. Sometimes the radiation compresses nearby gas, triggering the birth of new stars. In other cases, the energy disperses the cloud entirely, halting star formation. These interactions reveal that stellar heat is not simply a local phenomenon confined to the star itself. It shapes entire regions of space. Yet even the hottest blue stars are only part of the story. As massive stars evolve, their temperatures can change dramatically. After burning hydrogen in their cores, some stars expand into enormous red supergiants. Despite their reddish colour suggesting cooler surfaces, these stars can reach sizes hundreds of times larger than the Sun. Others follow different evolutionary paths and become even hotter in later stages. One striking example involves a type of star known as a Wolf-Rayet star. Wolf-Rayet stars are among the most extreme stellar objects known. They represent a late stage in the life of very massive stars. During this phase, powerful stellar winds blow away the outer layers of the star, exposing deeper, hotter regions beneath. The exposed surface of a Wolf-Rayet star can reach temperatures well above 100,000 degrees Celsius. At those temperatures, the star emits intense ultraviolet radiation and powerful stellar winds that carry material into space at astonishing speeds. These winds can shape surrounding nebulae into complex structures of glowing gas. Some Wolf-Rayet stars lose mass so rapidly that they shed enormous amounts of material over relatively short periods of time. The ejected gas forms expanding shells around the star, illuminated by the fierce radiation coming from its surface. Eventually, many of these massive stars reach a dramatic conclusion. When the nuclear fuel in the core can no longer support the star against gravity, the core collapses. In the moments before and during that collapse, temperatures rise to extraordinary levels. The resulting explosion, known as a supernova, releases more energy in a few seconds than the Sun will produce in its entire lifetime. During such events, temperatures can soar into the billions of degrees. But that stage belongs to a later part of the story. Before reaching the violent end of massive stars, there are still many remarkable details about how stellar heat operates within the stars themselves. Inside a star, heat does not simply remain in one place. Energy generated in the core must move outward through the surrounding layers. In the Sun, this happens through a combination of radiation and convection. Radiation transports energy as photons slowly scatter through the dense plasma. Convection occurs when hot material rises toward the surface, while cooler material sinks downward, creating enormous circulating currents. In larger stars, these processes can behave differently. Some massive stars mix their interior material much more efficiently, allowing fresh hydrogen to reach the core while heavier elements move outward. This mixing affects how long the star can continue burning fuel and how its temperature evolves over time. Astronomers study these processes carefully because they reveal how stars live and die. Understanding stellar temperatures also helps scientists interpret the light from distant galaxies. When astronomers observe the combined glow of billions of stars in another galaxy, they can analyze the spectrum of that light to determine the types of stars present. If the galaxy's light contains strong ultraviolet radiation, it suggests the presence of hot, massive stars. If the light appears redder, it may indicate an older population of cooler stars. Through these observations, scientists can estimate the age, composition, and history of distant galaxies. In that way, the heat of stars becomes a tool for understanding the structure of the universe itself. Despite their incredible temperatures, however, even the hottest stars represent only part of the thermal extremes that exist in space. Stars generate enormous heat through nuclear fusion, but certain cosmic events push temperatures even higher. For most of its life, a star maintains a delicate balance. Gravity pulls inward, trying to compress the star's enormous mass into a smaller and smaller space. At the same time, nuclear fusion in the core releases energy that pushes outward. As long as those two forces remain balanced, the star remains stable. It shines steadily, releasing light and heat across space. But that balance cannot last forever. Eventually, the fuel that powers the star begins to run out. In stars like the Sun, this transition happens slowly. Billions of years from now, the Sun will expand into a red giant and later shed its outer layers, leaving behind a quiet remnant called a white dwarf. Massive stars follow a much more dramatic path. When a star several times more massive than the Sun approaches the end of its life, the nuclear reactions in its core change in a rapid sequence. The star begins fusing heavier and heavier elements. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen and neon. Each new stage of fusion requires higher temperatures and pressures than the last. As the core contracts under gravity, temperatures rise to keep the fusion reactions going. For a time, the star manages to support itself this way, but each stage of fusion lasts for a shorter period than the previous one. Hydrogen burning might last millions of years. Helium burning may last hundreds of thousands. Later reactions involving heavier elements may last only years, days, or even hours. Eventually, the star begins producing iron in its core. Iron marks the turning point. Unlike lighter elements, fusing iron does not release energy. Instead, it consumes energy. Once iron accumulates in the core, the star can no longer produce the outward pressure needed to resist gravity. At that moment, the balance that supported the star for millions of years collapses. Gravity suddenly takes over. The core begins to fall inward with incredible speed. Matter that once moved slowly through the stellar interior now accelerates toward the centre at thousands of kilometers per second. As the core collapses, the density and temperature rise dramatically. Electrons are forced into atomic nuclei, combining with protons to form neutrons. The collapsing material compresses into an incredibly dense ball only a few tens of kilometers across. When the collapse finally stops, the core rebounds violently. The outer layers of the star, still rushing inward, slam into this suddenly rigid core. The impact creates an enormous shock wave that blasts outward through the star. This is the beginning of a supernova. The shock wave tears through the star's interior, heating the surrounding material to extraordinary temperatures. Nuclear reactions occur rapidly as the shock wave passes through each layer of the star. Elements heavier than iron are formed during these moments. Gold, uranium, and many other rare elements in the universe are created during supernova explosions. The intense heat and pressure allow atomic nuclei to capture particles and form new elements that would never appear in normal stellar fusion. Meanwhile, the star itself is being torn apart. The shock wave reaches the surface and ejects the star's outer layers into space at enormous speeds. For a brief time, the exploding star may shine as brightly as an entire galaxy. From Earth, supernovae appear as sudden new stars that brighten dramatically before fading away over weeks or months. Historically, several of these explosions have been visible to the naked eye. In the year 1054, observers in China and the Middle East recorded the appearance of a bright new star in the sky. For several weeks, it was visible even during daylight. Today we know that event as the supernova that created the Crab Nebula. The expanding cloud of gas from that explosion is still visible through telescopes nearly 1,000 years later. At its centre lies a neutron star, the collapsed core of the original star. During the explosion itself, temperatures reach astonishing levels. As the core collapses and the shockwave forms, temperatures climb to billions of degrees Celsius. These extreme conditions exist for only a short time, but they represent some of the hottest environments that occur naturally in the universe. Particles inside the exploding star move with tremendous energy. Atoms are stripped apart completely, and nuclear reactions occur in rapid chains. Radiation pours outward across the electromagnetic spectrum, from visible light to X-rays and gamma rays. The surrounding space becomes flooded with energy. Even after the initial explosion fades, the expanding debris cloud remains extremely hot. Shockwaves continue to heat the surrounding gas as the material ploughs through interstellar space. Astronomers often observe supernova remnants using X-ray telescopes. These instruments reveal clouds of plasma heated to millions of degrees as the shockwaves interact with nearby gas. Over time, the expanding debris spreads out across light years of space. Eventually it cools and mixes with surrounding interstellar material. Those enriched clouds of gas later become the birthplace of new stars and planets. The iron in your blood, the calcium in your bones, and many of the heavier elements around you were once forged in the heart of a dying star. Long before the solar system formed, ancient supernova scattered those elements across space. Our planet formed from material that had already passed through multiple generations of stars. Supernova explosions come in more than one form. The type described earlier occurs when a massive star collapses under its own gravity. Astronomers call this a core collapse supernova. Another type occurs in binary star systems involving white dwarfs. White dwarfs are dense stellar remnants left behind when smaller stars exhaust their nuclear fuel. These objects pack a mass comparable to the Sun into a volume roughly the size of Earth. In certain binary systems, a white dwarf orbits a companion star. If the two stars are close enough, the white dwarf can begin pulling gas from its companion. The stolen gas accumulates on the white dwarf's surface, slowly increasing its mass. There is a limit to how massive a white dwarf can become while remaining stable. This threshold is known as the Chandrasekhar limit. If the white dwarf's mass approaches this limit, the pressure inside becomes great enough to ignite runaway nuclear fusion. Unlike the steady fusion inside normal stars, this reaction spreads explosively through the entire white dwarf. Within seconds, the star is completely destroyed. This event produces a Type 1a supernova. The explosion releases enormous energy and briefly heats the stellar material to extremely high temperatures. Like core collapse supernovae, these explosions scatter heavy elements across space and produce expanding clouds of glowing gas. Astronomers study Type 1a supernovae carefully because their brightness follows predictable patterns. By measuring how bright these explosions appear from Earth, scientists can estimate distances across the universe. These observations played an important role in discovering that the expansion of the universe is accelerating. Even though supernova explosions are brief compared with the lifetime of stars, they represent some of the most violent and energetic events in the cosmos. The temperatures involved push matter into extreme states. At billions of degrees, atomic structure breaks down entirely. Nuclei collide with enormous energy, creating new elements and releasing powerful radiation. When a massive star reaches the end of its life and explodes as a supernova, the explosion scatters most of the star's material across space. Yet not everything escapes. Deep in the centre, the collapsing core of the star can remain behind as a compact remnant so dense and unusual that it behaves unlike any familiar object in everyday life. This remnant is known as a neutron star. Despite the name, a neutron star is not a typical star anymore. It no longer produces energy through nuclear fusion like the Sun does. Instead, it is the compressed core of a once massive star, a leftover object formed when gravity squeezed matter to extraordinary densities. To picture what that means, it helps to consider how extreme the collapse becomes. During the final moments before the supernova explosion, the core of the star shrinks dramatically. A region that once spanned thousands of kilometres collapses into an object only about 20 kilometres across. That is roughly the size of a city. Yet the mass of the core remains enormous. A typical neutron star may contain more mass than the Sun. That means an amount of matter comparable to the entire solar system's central star has been squeezed into a sphere no larger than a small metropolitan area. The resulting density is almost impossible to imagine. If you could scoop up a teaspoon of neutron star material and somehow bring it to Earth without it exploding apart, that tiny amount would weigh billions of tons. The matter inside neutron stars is compressed so tightly that the usual structure of atoms can no longer exist. Under these conditions, electrons are forced into atomic nuclei, combining with protons to form neutrons. The star becomes essentially a giant ball of neutrons packed together in an extremely dense arrangement. That is where the name comes from. But density is only part of the story. When a neutron star first forms in the aftermath of a supernova, it is incredibly hot. The collapse that created it released enormous gravitational energy. Much of that energy heated the newly formed neutron star to extraordinary temperatures. In the moments immediately after formation, temperatures in the interior can reach around 100 billion degrees Celsius. That is far hotter than the core of any ordinary star. At those temperatures, the matter inside the neutron star exists in a state far beyond the familiar forms of solid, liquid, or gas. Even plasma, which dominates the interiors of stars like the Sun, does not fully describe the behaviour of matter under such extreme compression and heat. Physicists are still working to understand exactly how particles behave inside neutron stars. Some theories suggest that the neutrons themselves may break apart into their fundamental components, forming an exotic mixture of particles sometimes referred to as quark matter. Whether this occurs depends on conditions that remain difficult to study directly. What scientists do know is that neutron stars cool over time. After the supernova explosion fades, the newborn neutron star begins radiating energy into space. The outer layers cool gradually, dropping from billions of degrees to millions over the course of thousands or millions of years. Even after this cooling period, however, neutron stars remain extremely hot by human standards. The surface temperature of a young neutron star may still reach several million degrees Celsius. At those temperatures, the star emits powerful X-rays that can be detected by space telescopes. Astronomers observe these X-rays to study neutron stars across the galaxy. Because neutron stars are so small and distant, they usually appear as faint points of light even in powerful telescopes. But their radiation carries information about their temperature, magnetic fields, and rotation. Rotation is another remarkable feature of these objects. When the core of a star collapses into a neutron star, its rotation speeds up dramatically. This happens for the same reason an ice skater spins faster when pulling their arms inward. As the collapsing star shrinks to a tiny fraction of its original size, its rotation rate increases. Some neutron stars spin dozens or even hundreds of times per second. This rapid rotation, combined with extremely strong magnetic fields, creates one of the most fascinating phenomena in astrophysics: pulsars. A pulsar is a rotating neutron star that emits beams of radiation from its magnetic poles. These beams sweep across space as the star spins. If one of those beams crosses Earth, astronomers observe a regular pulse of radiation each time the beam passes our line of sight. The pulses can be astonishingly precise. Some pulses rotate hundreds of times per second, producing pulses as regular as the ticking of a clock. In fact, certain pulses are so stable that they rival the accuracy of atomic clocks on Earth. The radiation emitted by pulsars often includes X-rays and gamma rays, indicating extremely energetic processes near the star's surface. Part of this energy comes from the star's powerful magnetic field. Neutron stars possess the strongest magnetic fields known in the universe outside of black holes. These fields can be trillions of times stronger than Earth's magnetic field. Such intense magnetism affects the behaviour of charged particles around the star. Particles trapped by the magnetic field accelerate along field lines at incredible speeds. As they move, they emit radiation across a wide range of wavelengths. The resulting glow reveals how energetic the environment near the neutron star can be. In some cases, neutron stars become even more extreme. A special category known as Magnetars possesses magnetic fields thousands of times stronger than ordinary neutron stars. The magnetic energy stored in these fields can twist and fracture the crust of the star itself. When that happens, enormous bursts of energy are released. These events, known as starquakes, can produce intense flashes of gamma rays detectable across large distances in the galaxy. During such outbursts, temperatures near the star's surface may briefly climb to extraordinary levels as energy spreads through the surrounding plasma. Even though neutron stars are tiny compared with ordinary stars, their influence can extend far into space. Some neutron stars exist in binary systems, orbiting close to another star. If the neutron star's gravity begins pulling gas from its companion, the stolen material forms a swirling disk around the neutron star. This situation resembles the accretion disks found around black holes, though the physical processes differ slightly. As gas spirals inward toward the neutron star, friction heats the material dramatically. Temperatures in the accretion disk can climb into the tens of millions of degrees. The hot plasma emits X-rays that astronomers detect using specialized space telescopes. These X-ray binaries provide important clues about how matter behaves under extreme gravity and temperature. Occasionally, the accumulated gas on the neutron star's surface ignites in sudden bursts of nuclear fusion. These events, known as X-ray bursts, release tremendous energy in a matter of seconds. During the burst, temperatures can briefly rise to billions of degrees before settling back down. Such bursts demonstrate that even long after their violent birth, neutron stars can still produce moments of extraordinary heat. Yet despite their extreme temperatures and dense structure, neutron stars are not the final stage of stellar collapse. Neutron stars already represent some of the most extreme objects in the universe. Their density is staggering, their magnetic fields are immense, and the heat they produce during their formation reaches extraordinary levels. Yet there exists another kind of cosmic object where matter can experience even more intense conditions. That object is a black hole. The name black hole can make it sound like a simple empty space, as though it were merely a hole punched into the fabric of the universe. In reality, a black hole is anything but empty. It's a region where gravity has become so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. Black holes form when extremely massive stars collapse at the end of their lives. If the collapsing core contains enough mass, gravity overwhelms every force that might resist it. Instead of stabilizing as a neutron star, the matter continues compressing until it becomes a black hole. The event horizon marks the point where escape becomes impossible. Anything that crosses this boundary can never return to the outside universe. Despite this dramatic description, black holes themselves do not glow. If a black hole existed entirely alone in empty space, it would be invisible. There would be nothing to reveal its presence except its gravitational influence on nearby objects. But most black holes are not completely isolated. In many parts of the universe, black holes are surrounded by gas, dust, or even entire stars. When matter begins falling toward a black hole, something remarkable happens. The material does not plunge directly inward all at once. Instead, it begins to spiral. As gas approaches a black hole, it forms a rotating structure known as an accretion disk. This disk is made of material gradually moving inward, orbiting the black hole while losing energy through friction and collisions between particles. The word disk might suggest something thin and quiet, but in reality these structures are among the most violent environments in the universe. The gas within an accretion disk moves at incredible speeds. Near the inner regions of the disk, matter may orbit the black hole at a significant fraction of the speed of light. As particles race around the disk, they collide constantly with neighbouring particles. Each collision converts some of the particles' motion into heat. With trillions of collisions happening every second, the temperature of the disk rises rapidly. The result is one of the hottest naturally occurring environments known in the cosmos. Temperatures in the inner regions of accretion disks around stellar mass black holes can reach tens of millions of degrees Celsius. At these temperatures, the gas becomes an extremely energetic plasma that emits powerful X-rays. Astronomers detect these X-rays using space telescopes designed specifically for that purpose. Observatories such as NASA's Chandra X-ray Observatory and ESA's XMM Newton telescope allow scientists to study the glowing disks surrounding black holes across our galaxy. The X-ray radiation produced by accretion disks reveals how matter behaves as it approaches the most extreme gravitational environments. In some systems, the black hole is part of a binary pair with an ordinary star. Over time, the black hole's gravity can pull gas away from its companion. This stolen gas forms the accretion disk, gradually spiraling inward toward the event horizon. These systems are known as X-ray binaries because the heated gas in the disk emits strong X-ray radiation. From Earth, the black hole itself remains invisible, but the glowing disk surrounding it reveals the intense activity taking place there. The closer gas gets to the black hole, the faster it moves and the hotter it becomes. Near the inner edge of the disk, the particles are so energetic that the plasma radiates enormous amounts of energy into space. The heat generated in these regions can rival the temperatures found in the cores of stars. In fact, the energy output of an accretion disk can sometimes exceed the energy produced by nuclear fusion in a star of similar mass. Gravity alone powers this process. As matter falls deeper into the black hole's gravitational well, gravitational potential energy is converted into heat and radiation. The closer the material moves toward the event horizon, the more energy is released. This process can be remarkably efficient. In some cases, the conversion of gravitational energy into radiation around black holes releases more energy per unit of mass than nuclear fusion itself. But stellar mass black holes are only part of the story. At the centres of most galaxies, including our own Milky Way, there exist black holes millions or even billions of times more massive than the Sun. These are called supermassive black holes. When large amounts of gas fall toward a supermassive black hole, the resulting accretion disk becomes truly enormous. The disk may stretch across distances comparable to the size of the solar system, or even larger. Temperatures within these disks can vary dramatically depending on the distance from the black hole. Outer regions of the disk may glow in visible light, while the inner regions become hot enough to emit ultraviolet radiation and powerful X-rays.